In this video, we're going to do example 7.5.1. Let x and y have joint density function given here. Find the expected value of x times y. X times y is a function of x and y, and so we're going to use the bivariate lotus. So the expected value of x times y is the integral from minus infinity to infinity of the integral from minus infinity to infinity of our function xy times the density function f of xy dy dx. Now to replace the double integral from infinity to infinity, we need to use the correct support, and so let's draw that here. So the x values go from 0 to 1, and the y values go from 0 to 1 minus x, so we've got this line y is equal to 1 minus x, and this is the support that we're integrating over here. And so we end up by integrating from 0 to 1 of the integral from 0 to 1 minus x of our function xy times the density. That's 24xy dy dx. We can clean up the integrand. So integral from 0 to 1, integral from 0 to 1 minus x of 24x squared y squared dy dx, which is a double integral that we've evaluated. Well, maybe not exactly this one, but something very similar many times so far. So we'll leave out the details of this. You can evaluate on your own to check if you want, but I got 2 over 15. So that is the expected value of a function xy. What about the variance? So part B, we're asked to calculate the variance, and we've got to remember the computational formula. So if we have a single variable e of x, not e of x, v of x, well that is the computational formula for variance, e of x squared minus e of x all squared. And so what we can do is just replace xy in for the x's, which means that we are looking to evaluate here the expected value of xy squared minus the expected value of xy all squared. Now this value is what we have up here, so we can take that and square it as our next term. But we have to evaluate the expected value of xy squared. And so that is going to be another application of the bivariate lotus. So the expected value of xy squared is the double integral minus infinity to infinity of the function xy squared times the density times f of xy dy dx. Now this, again with the correct bounds, is from 0 to 1, and from 0 to 1 minus x, we get x squared y squared times the same density, 24xy dy dx. And so cleaning up the integrand, we have the integral from 0 to 1, the integral from 0 to 1 minus x of 24 x cubed y cubed dy dx. Again, we'll skip the details of the integration. I got 3 over 140. 3 over 140, you can double check that on your own if you want, but that's the value that's going to go right up into here. So for our variance, we are going to have e of xy squared is 3 over 140 minus e of xy all squared. Well, e of xy was this value from part A, so 2 over 15 squared, and evaluating that, we'll get 23 over 6,300. So that is the variance of this xy. So what if we wanted the sigma? So for example, right, we might say that this is another random variable t. This is v of t, which is v of xy. What if we wanted sigma of t? Well, that would just be the square root of the variance, which would be the square root of 23 over 6,300. Last, part C here, what if we want to find the expected value of x? Now that looks a little bit strange because that's a single variable, but we have a bivariate situation, right? We've got two jointly distributed random variables. We've got joint density function. So we can certainly apply the bivariate lotus function by imagining that this is just a function h of xy that's just equal to x. And so we can evaluate e of x as the same double integral from minus infinity to infinity on each of them of our function x times the density function. So replacing, as we've done in the previous two parts, the integral from 0 to 1, the integral from 0 to 1 minus x of x times 24xy dy dx, which is the integral from 0 to 1, the integral from 0 to 1 minus x of 24 x squared y dy dx, and this, when I evaluated it, gave me 2 over 5. Now this, you might say, well, okay, but sure, this works, but this is a single variable. What if this were just sort of on its own? What if I didn't think about this, and what if I wanted to use the univariate formula? If I wanted to say, well, the expected value of x is the integral from minus infinity to infinity of x times the density function of x dx. What about that formula? How can I be sure that these two things will give the same value? And that is an excellent question, and we will answer that in the next video by looking at a little theorem.